Welcome to the lecture number 24th of the course Extra High Voltage AC and DC Transmission System. So in the previous lecture we discussed the advantages and disadvantages of HVDC system, and then we, based on the applications, we studied the three classifications of HVDC system, that is back-to-back HVDC transmission for bulk power transfer, back-to-back for control of power, and long distance HVDC transmission, and the third was modulation of AC. Now next, coming to the types of HVDC links. How many types of links we have? We have three types of HVDC links. So the first type is the monopolar HVDC link. Monopolar means only one pole. Monopolar means one pole. Here pole means conductor, means only one conductor for power transfer is used, and the return path and the return conductor, for return path we are using earth. Okay, means it is a diagram I am showing it here. Suppose I have two converters at two stations. Okay, and both the converters, they are here connected to AC systems. So what we are doing, we are using only one conductor for power transfer. Okay, and the return is through the ground or through the earth. This is called monopolar link or monopolar line. So the tower structure is shown like here. Here we have a tower. We have a single cross arm where we have only one cross arm where we have only one conductor. This is the point where conductor is fixed to the tower. Okay, this circle here, it represents conductor cross section. So this is the monopolar link, which uses only one energized conductor, and the energized conductor, the polarity that is preferred in monopolar link, generally negative polarity is preferred. Why negative polarity is preferred? So because in negative polarity the corona losses are less as compared to a positive polarity. Also, if with negative polarity, since we are using ground as the return path, it is also possible that some communication lines, they may also be buried in the ground, or some communication lines, they may also be using the earth as the medium. Okay, so it is possible that this return path may interfere with those communication lines. Okay, so if we are taking a negative polarity, the interference level will be less in communication lines. So it uses only a single conductor for power transfer, and that conductor is of negative polarity, and this negative polarity is preferred due to low corona loss and reduced radio interference. As you can see that ground is used as the return path. Now this ground, it creates problem. What problem can it create? Suppose there are certain metallic bodies that are buried inside the earth. Okay, like maybe there are these PHE pipes, concrete, steel pipes. So what will happen, or any other metallic body that is buried inside the earth? So what will happen, this when power will return through this ground path, it will induce voltages in those metallic bodies. Okay, and which may cause corrosion. Okay, so these metallic bodies, when they will get electrocuted, they will get corroded as well. So that is a disadvantage. The second disadvantage is that in case the ground is through some sea or through some water body or lake, in that case it can affect the aquatic life as well. So these are the disadvantages of using the ground. So as you can see, there is only one path, and ground is used as return conductor. So in case of any problem at the converter station or in the line, in case of any problem, the power supply will be interrupted. Okay, so suppose we are saying that there is some power means at this converter station there is some problem, there is a fault. So we have to take out this line, and in that case the power flow will be interrupted. There will be no power flow during that time. So this is the disadvantage of this monopolar link, means it is less reliable. Okay, so reliability is very less. In case of any fault or any abnormal condition, the power flow will be interrupted. Okay, and also since only one conductor is used, so the power transfer capacity is also low. Okay, the power transfer capacity is also low. So these disadvantages like less reliability in case of problems because of ground, these problems are overcome in second type of HVDC link, that is called bipolar HVDC link. Remember, bipolar HVDC links are used. Okay, they are used, preferred. Like we have Rihan Dadri HVDC link. I think it is operating at plus minus 500 volts, kilovolts, sorry. Plus minus 500 kilovolts means the voltage can be changed from minus 500 to plus 500. So if you can see, it will be 1000 kilovolts. Minus 500 to 0, and from 0 to plus 500 it is 1000 volts. So bipolar HVDC links are preferred. Normally, how a bipolar HVDC looks like? It looks like we have one link here and another link here. Okay, so we are using two conductors, one for transferring power and the other conductor, it acts as ground. That is why I am writing here plus and minus. So this conductor, it is at a voltage, operates at a voltage plus 500, and this will operate at a voltage minus 500. But you can change the operation. You can by controlling the pulses, you can make this conductor to operate at plus 500 and this conductor to operate at minus 500. Okay, it is easily it can be done easily. And the tower structure will be like this. We have a tower and we have two cross arms and we have two conductors. One is the conductor from where we are transferring the power, and the another conductor is the return conductor. So as you can see, I am saying it is plus minus 500, means this conductor is at minus 500 and this conductor is at plus 500. So voltage, total voltage from this end to this end, it is minus 500 to plus 500, it is 1000 kilovolt. Okay, so from this point to this point, I will say it is 500 kilovolt. I will write VDC by 2, and from this point to this point it is 1000 kilovolt VDC. That's why we are representing the voltage of the bipolar HVDC link as plus minus VDC. Plus means minus VDC to plus VDC, minus VDC to plus VDC. Okay, so this type of bipolar HVDC link, it uses two poles of opposite polarity. One is positive and the other is negative. So and under normal condition, the current flows from the positive, power flows from this positive conductor and returns through the negative conductor under normal operation, and the current through the ground is 0. Okay, however, in case there is a fault in any of the conductors, suppose in the positive link, I am saying there is a fault here, or fault at this converter, or fault at this converter. These converters can be taken out. Means this line can be taken out and still power can be supplied through the other link. Okay, but as you can see, if I am taking out, suppose I am taking out this lower line, I am taking out this link out because I am saying there is a fault at this point. I am taking out this link. Then still half of the power can be transferred through this link, and the return will be through ground at that time. Okay, because as you see, if the return is through ground, what will the voltage? Voltage will be VDC by 2. Obviously, power is VDC into IDC. So if the voltage will reduce by half, the power will also reduce by half. So in case of any fault in any of the link, I am saying that still half of the power can be transferred. Okay, and the return will be through ground, but only in emergency condition. However, under normal condition, what will happen? Same current will flow through both the conductors. Okay, same current will flow through both the conductors, and the current through the ground is 0 in case of normal conditions. So let me start next. So that is what I am writing. A bipolar HVDC has two circuits which are almost independent of each other. Both the circuits operate independently. Only under emergency condition current through earth is allowed. Otherwise the bipolar mode of operation is preferred. You know, when current flows through the ground, if I am taking one of the links, I am taking out one of the conductor, in that case current will flow through the ground. Return current will flow, return path is through ground. So in that case, the bipolar HVDC link will act will act like a monopolar HVDC link, but only under emergency condition. Under emergency condition, a bipolar link operates like a monopolar link. Okay, and half of the power is still transferred. That is why we are saying that since half of the power can still be transferred, that is why we can say that this type of link, that is a bipolar HVDC link, it is more reliable as compared to the polar HVDC link. Okay, so also the problem that were arising in the monopolar HVDC link because of the because of the Earth as the return path, those problems will not arise in case of a bipolar HVDC link if operating under normal condition. However, if it is operating under some emergency condition where we are using Earth as the return path, in that case, the same problem, Earth problems which were discussed in the monopolar HVDC link, they will be faced in this link as well under emergency condition. Okay. Now, the third type of HVDC link, it is called a homopolar. Mono means one polar, bipolar means two pole. Homopolar, it also means two poles, but of same polarity. In bipolar, we were using one positive pole and another negative pole. One line positive and other line negative. However, in homopolar, we are using two lines, but both the lines are of same polarity. And negative polarity is preferred here, again, due to reduced coronal loss and reduced interference. Okay, so since both the poles are of same polarity, means both the poles are of same polarity, therefore what will happen? Then in that case, the return will be again through the ground. Okay, during normal as well as abnormal conditions. So in homopolar HVDC link, return path is always through ground, both during normal as well as emergency condition. So when ground is used as a return path, it gives problems like interference, okay, corrosion of metallic bodies that are buried inside, means harmful effects on aquatic life if the return is through sea or some water body. Okay, just a minute. Yeah, let me show you the diagram of this. Okay, yes. So in case of this is a diagram for a homopolar, means power is flowing from this end to this end and returning to ground, and here the power is flowing from this end to this end and returning to ground. Power is flowing like this. Okay, so again, power supplied will be same as that which is supplied in the bipolar link. Okay, but the problem is that Earth is used as a return path always. Okay, so in case and failure, there is any failure in any link, the half of the power can still be transferred to the another link, means reliability is still more than homopolar, but still it has got some problems because of this return path. So that is why it is not preferred. It is not always preferred. Okay, so normally any HVDC station system you see in the world, it is a bipolar link like Rihan Dadri, okay, which operates at plus minus 500 volt. Here I am saying this is operating at negative polarity, this is also a negative polarity, so it is represented as minus or simply minus 500 kilovolt, minus 500 kilovolt, minus 500 kilovolt, or simply minus 500 kilovolt. Okay, means minus 5 from this to this voltage is minus 500, and from this to this voltage is minus 500 kilovolt. I missed few points regarding this bipolar HVDC link. Actually, I skipped this page. So I was saying in a bipolar that in case of problem in any pole, still half of the power can be transferred through the another link. Okay, so that means ground is used as a return path only during emergency condition in case of a bipolar link. Okay, so at each terminal, whether I am talking about bipolar or homopolar, at each terminals we have two converters of equal rated voltages, means we are using two converters on one side and two converters, like two converters here and two converters here. These two converters are of equal voltage rating. Okay, they have the same voltage rating and they are connected in series. Okay, They are connected in series to the DC side. So if current in the two poles, this is one pole and this is one pole and this is the another pole. If current in these two poles are equal, what will the current through the ground? The current through the ground at that time will be 0, and means when the current through the ground is 0, we say that the bipolar link is operating under normal condition. Okay, and the rated voltage of a bipolar link, it is given by plus minus VDC. Plus minus VDC. Rated voltage of a bipolar link is given by plus minus VDC. For example, a Rihan to Dadri HVDC bipolar link which operates at a voltage of plus minus 500 kilovolt, or simply we can say 1000 kilovolt. Okay, so this is all about the monopolar, bipolar and homopolar links. Means that types of links that are used. So you will see that a two pole line is cheaper. A two pole line, whether bipolar or homopolar, it is cheaper as compared to a three-phase double circuit AC line. Whether it is in terms of insulation cost, whether it is in terms of more power transfer or less installation cost, we will see. So in that case, in today's lecture, we studied three types of link: mono, bi, homo. In monopolar, one pole was used and negative polarity was preferred, and the return was through the ground, which creates certain problems which we discussed. Okay, in case of bipolar, two poles of opposite polarity were used. Okay, and the voltage rating of the link was given by plus minus VDC. Okay, so one was positive pole, another was negative pole. Okay, and obviously the power that can be transferred in bipolar, it is more than the monopolar. It is 2 times the monopolar. And in case of fault in any one pole, the half of the power can still be supplied from the other pole, but in that case current through the ground will flow, which will give certain problems. Now in case of a homopolar HVDC link, again two poles were used, but both the poles were of the same polarity. Okay, so if both the poles were of the same polarity, means both were the means return path was not there, so obviously the return will be through ground at that time. Okay, means under normal operation or emergency operation, homopolar HVDC links, in homopolar HVDC link, return is always through the ground. And in case of fault in any one link, the half of the power can still be transferred through the another link. But the problem in homopolar is that is the ground. It gives certain problems. Okay, so so that is why instead of homopolar, we are using bipolar HVDC link. Now let us do a simple economic comparison between a HVDC system, bipolar HVDC system, and a three-phase AC system. Simple economic comparison. Okay, so I am saying economic comparison between AC and DC system, and for doing any comparison we need certain assumptions or certain things which are common. So this is a three-phase system, balanced three-phase system. I'm saying voltage in each phase is VAC. It is a balance, so voltage in each phase will be VAC, and the current in each phase will be IAC. Okay, VAC means AC voltage and IAC means AC current. And this is a bipolar HVDC link I am taking. So this is the voltage from this point to this point is VDC by 2. From this point to this point it will be VDC. Current through the link will be IDC. It is a bipolar HVDC link. No, I am making certain assumptions, and the assumptions are like that. I am saying that the power transfer in both, the links will be same. In AC and DC, we are transferring the same amount of power, and we are assuming that the losses in both the system are same and the conductor size in both the systems are same. Now we will see how this is economical as compared to this in terms of insulation cost. Okay. So the first assumption, I am saying that power AC is equal to power DC. Same power is flowing. So power transferred in DC will be VDC into IDC. Okay, VDC from this to this, it is VDC. From this point to this point, this point to this point, voltage is VDC. So the power will be VDC into IDC. Equation 1. So what will be the power transferred in the in AC? So it is three phase. So I will write 3 IAC into VAC, taking power factor as unity. 3 IAC into VAC. I am saying both the powers are equal. So equating these two equations, I will get VDC by VAC is equal to 3 multiplied by IAC by IDC. Okay. This is from the power equation. That same power is flowing, where we are assuming power losses and conductor size is same. So this is one assumption. I got an equation that VDC by VAC is equal to 3 into IAC by IDC. Now the second assumption that we are saying that the DC losses are both in the same same in both the systems. So I am saying what will be the DC loss? How many conductors are there? There are 2 conductors, 1, 2, and same current is flowing in both the conductors, and each conductor has a resistance R. So what will be IDC, I square R in this and I square R in this. So it will be IDC square into twice R, IDC square into twice R. So 2 IDC square into R. What will be the losses in AC? I have 3 phases. Okay, the current in this phase is IAC and the resistance of this line is R. The current in this is a balanced system, so current in each phase will be IAC and the resistance of each line will be same. So what will be the total losses? It will be 3 IAC square into R. 3 IAC square into R, because IAC square into R is the loss in one phase. So in 3 phase we have a loss of 3 IAC square into R, and we have an assumption that both the losses are same. So twice IDC square R will be equal to thrice IAC square into R. So IDC by IAC will be root 3 by 2. So this is my equation 4. I will substitute this in equation number 3. Here I have equation number 3. VDC by VAC is equal to this. So I know I have calculated IDC by IAC. I will substitute in this equation. So if I will substitute here, I will get VDC upon VAC is equal to 3 multiplied by root 2 by 3, which is equal to root 6. Okay. So which voltage is more? Obviously, DC voltage will be more or AC voltage will be more. We are multiplying DC voltage by root 6 times AC. Okay, then we are getting VDC. Okay, so then we are saying the DC insulation level is designed. You know, insulation level, if you increase the insulation level, or if you will use better insulation, then you can increase the voltage handling capacity. If you will provide better cooling, you will increase the current handling capacity. Okay. So DC insulation level is designed to withstand a voltage. What this conductor, it is subjected to which voltage? From ground to this, look at it is VDC by 2. Okay, and this conductor, it is also subjected to a voltage VDC by 2 from this point to this point. Okay, so we are saying that DC insulation level is designed to withstand a voltage of VDC by 2. Okay, so we are saying VAC is the VAC is the AC voltage. So but we are designing the AC for the peak value. So what will be the peak value here? This is the RMS value. Peak value will be root 2 into VAC. So for AC, we are designing the AC for an insulation of level of root 2 into VAC. Root 2 into VAC. So we will take the ratio of the DC insulation divided by AC insulation. It will be VDC by 2 multiplied by root 2 VAC. We also know VDC by VAC, we calculated it is root 6. Substitute it here. We will get DC insulation by AC insulation level is equal to 0.866. Means DC insulation level is 0.866 times the AC insulation level. Means DC insulation level is lower as compared to the AC insulation level. So if the DC insulation level is lower as compared to AC insulation level, so cost of the insulation will reduce in DC. However, the cost of the insulation in AC will be more. So we are saying DC insulation level is 13.36% less as compared to the AC insulation level. Therefore, cost of insulation is less in DC as compared to AC. That is why we say DC is economical as compared to AC, but for long distances. Okay, so this is the one comparison I am showing you here. Okay. So in next class we will do 2 more comparisons. So this is based on the insulation level now. We are saying in case of AC, less insulation is required. So the more the insulation, the more the cost. Okay. So why? That is why we are saying now that we are generating the power is generated always at 11 kV. 11 kV because if we increase the voltage, we need better insulation in generators. So that insulation, it increases the insulation cost. Okay. So that is why we are generating it at 11 kV. So that is all for today's lecture. Okay. Please go through these notes. And in case of any doubt, call me or just write a comment in the Google Classroom. Thank you very much.